Alright, welcome back. So, bit of a break there, but last time we had set up our fix functions and created our create graphics pipeline function and ran through all that, which was reading the shader code, reading it as binaries into memory, and then creating shader modules from that. And now we are on to creating the actual render pass, or passes. Alright, so let's just, again, as is tradition, with myself, let's check everything works fine, and it does. We can close that and it all seems to be fine. Cool. All right, so before we start, let's get some music on. Ooh, it's a bit loud. All right, so before we can finish creating the pipeline, we need to tell Vulkan about the frame buffer attachments that we will be using while rendering. We need to specify how many color and depth buffers there will be, and how many samples to use on each of them, and how their contents should be handled, blah, 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 blah. Okay, all of this information is wrapped up in a render pass object. Okay, so we'll create a create render pass function just to be called underneath create graphics pipeline. All right, create graphics pipeline. Oops. Let's do this here. It's undoubtedly going to take an app. Create graphics pipeline. I'm calling it there. Do there. Create graphics pipeline. Let's just call it here. Takes an app. Point it to p app. All right. Review, we're all kind of set up. Oh, while I'm here, cheers. That is a large wine. All right. Attachment description. In our case, we'll have just a single color buffer attachment represented by one of the images from the soft chain. So let's add this to our function. And yep, okay, subchain format, that comes from papp, I believe. Yeah. So I'm kind of, just as a quick aside, I'm kind of torn between whether I like this setup, where you create a sort of zeroed out, I think it is, unless you have to do that, zeroed out struct, where everything is a falsy value, so like the integer 0, or false, or nil, null, different language. Or doing it this way, where I just specify, I speak, and then do it like this. I'm not really sure which is the better, more readable. Don't think it really makes much difference. I think any performance implications are like probably non-existent due to compilers being so goddamn smart. But because this is one massive file, I'm going to just do a mixture and see how I feel about it. So, you know, there you go. Talking to myself, I was, and still am. Okay, the format of the color attachment should match the format of the subchain images. Okay, and we're not doing anything with multi-sampling yet. So let's do this. Okay. All right, the load up and store up determine what to do with the data in the attachment before rendering and after rendering. We have the following choices for load up, up clear, don't care. For store, we have store and don't care. No one really cares. We're interested in seeing the rendering triangle, the rendered triangle on the screen, so we're going to stall operation here. Okay. So load, preserve the existing contents of the attachment. Clear is clear the existing contents. And don't care as existing content is undefined. We don't care about them. Okay, store. Rendered contents will be stored in memory and can be read later on. Or for don't care, the contents of the frame buffer will be undefined after the rendering operation. Okay. So for this, we're going to go with, for stencil, load and store ups, we'll go with this. And for our for our initial and final layouts, it looks like we go with undefined initially. Okay, textures and frame buffers in Vulkan are represented by a VK image objects with a certain pixel format. However, the layout of the pixel in memory may change based on what we're trying to do with the image. Okay, some of the common options are attachment optimal. Images are images used as color attachment. Present source KHR, images to be presented in the swap chain. And destination transfer destination optimal. Images are used as destinations for the memory copy operation. We'll discuss this more in the next chapter. Blah, blah, blah. The initial layout specifies which layout the image will have before the render pass begins. Okay, so before the render pass begins, which come with undefined, final layout specifies the layout to automatically transition to when the render pass finishes. Using VK undefined for layout, initial layout means that we don't care. Yep, this makes sense. I want to present the swap chain after rendering. Okay, that's fine. So we just go with this. I'm just going to bunch those all together because they're all the same thing. Whoop. All right. Subpasses and attachment references. A single render pass can consist of multiple subpasses. Subpasses are subsequent rendering operations that depend on the contents of the frame buffers in previous passes. Okay, so you can reuse stuff from previous passes. Interesting. For example, a sequence of post-processing effects that are applied one after another. Okay. If you group these rendering operations into a render pass, then Vulkan is able to reorder the operations and conserve memory bandwidth for possible better performance. For our very first triangle, however, we'll stick with a single subpass because we're not doing a huge amount of stuff. Okay, except the huge amount of code. Every subpass references one or more of the attachments that we've described using the structure of the previous section, VK attachment reference. Alright. Copy and the pasta. And again, I'll go with this. Attachment parameters specify which attachment to reference by its index attachment description array. Our array consists of a single VK attachment description, so it's index 0. Alright, the layout specifies which layout we would like to use attachment. Okay, blah blah blah. We intend to use attachment of the function as a color buffer, and the VK image layout color attachment optimal layout will give us the best performance, as the name implies. Alright, the subbus is described using a VK description structure. So, that's all good. Vulkan may also support compute subbuses in the future, but they don't yet. So we have to be explicit that we want this to be a graphics, bind point graphics. Next, we specify the reference and the color attachment. Alright, the index of attachment in this array is directly referenced by the fragment shader with the layout. Okay, so because we've got only one, the index is 0, so we just hard-coded it as 0 in the shader, in the fragment shader. The following other types of attachment can be referenced by a subpass. Input attachment, attachments that are read from the shader. Resolve attachment, attachments used for multi-sampling color attachments. Stencil attachment for stencil data. Preserve attachment, attachments that are not used by this subpass but for which the data must be preserved. Maybe using a different subpass. Okay, on to render pass. Now the attachment and a basic subpass reference is being described. Excuse me. We have to create a render pass itself. So we want to create a variable called VK render pass and VK pipeline layout on our struct app, which I didn't find just then, but hey ho. Whoops. Okay. Oh, come on, man. Copy that. There you go. Oh, we already have that. That's interesting. Okay. The render pass object can then be created by filling in the VK create or whatever pass create info struct. All right. So back down here, let's copy that. Where the hell were we? We were in the function of create render pass. So So all the way down here. Let's reorder that. So we've got our render pass info, type attachment, the color attachments we created up here, all the way up here. And then let's just do our app, p-app, passing in our device, the render pass info pointer, null, and the render pass, which is on the app. And here we'll just print f, and whoops, and we're going to exit with what we got. What are we up to? 8 by the look of it. Yeah, okay, great. Just like that, the pipeline layout. Just like the pipeline layout, the render pass will be referenced throughout the program, so we should only be cleaned up. It should be cleaned up at the end. Okay, let's clean that up. VK destroy render pass beneath the pipeline. Okay, VK destroy render pass. P app. Ooh. Device and p app render pass and null for no reporting. Okay, this was a lot of work to set up. Here it was. Now let's create a graphics pipeline object. Boom. But now let's just quickly test it runs. Sure does. Excellent. All right, cheers to that. Conclusion. Ooh. We can now combine all of the structures and objects from the previous chapters to create the graphics pipeline. Finally. Here's the type of object we have now as a quick recap. Okay, we've got the shader stages, the shader module that define the functionality of the programmable stages of the graphics pipeline. Fixed function state, all of the structures that define the fixed function stages of the pipeline, like input assembly, rasterizer, viewport, and color blending. Pipeline layout, uniform and push values referenced by the shader that can be updated at draw time, and the render pass. The attachments referenced by the pipeline stages and their usage. Pretty slick. All of these combined fully define the functionality of the graphics pipeline, so we can now begin to fill in the VK graphics pipeline create info struct at the end. Graphics pipeline, okay, at the end of the graphics pipeline function. But before all the calls to VK destroy shader mobile, okay. So at the bottom of this function, let's do this. Create graphics pipeline. Create graphics pipeline. The very bottom of our pipeline function, which is full of all of these many things. And before we do the cleanup, and I've just noticed that there's some weird formatting there. Okay. So we've now got a pipeline info struct started. Okay, we start by referencing the array of the pipeline shader. Yep. Shader stages, which we've got up here. And then we go, ooh, look at all these. Doing it this way, where we create the zeroed out struct, makes it easier to copy and paste based on what was done in this tutorial, that's for sure. Rasterizer. Where's our rasterizer? Oh, it's here. Oh, gotta give it the right name. And null. Alright. And then we reference all of the structures describing the fixed function state, and then the actual pipeline layout. Where be the, oh, that's on our p app. Cool. After that comes the pipeline layout, which is a Vulkan handle to our app struct, and then the render pass and the subpass index. I'm assuming that's the index. And finally, we have the reference to the render pass and the index of the subpass. If I had to just read ahead tiny bit, it would work. It's also possible to use other render passes with this pipeline instead of the specific instance, but they have to be compatible with render pass. Okay, the requirements for compatibility are described here. All right. We'll be using this feature in the tutorial. Grand. Again, that's on our app. Excuse me. And then finally, or nearly finally, there are actually two more parameters: base pipeline handle and base pipeline index. Vulkan allows you to create a new graphics pipeline for deriving from the existing pipeline. Oh, okay. So a pipeline of pipelines. The idea of pipeline derivatives is that it is less expensive to set up pipelines when they have, it's like shared functionality, okay. So you can switch between pipelines from the same parent, but also be done a lot quicker. Okay, you can either specify the handle of an existing pipeline with base pipeline handle, or reference another pipeline with the, whatever. These values are only used if the VK pipeline create derivative bit flag is set between is specified in the flags field. Okay, but we aren't doing that. We actually are doing more like this. Oh. Flags. All right. So finally, here we go. Now prepare for the final step of creating a class member. All right. And remembering that we are in the function of the massive function to create graphics pipeline. Oh my god. VK pipeline graphics pipe. Okay. All the way down to the bottom. Yeah. Likely here. So if VK create graphics pipeline, plural, device, p-app device. Oh, all the wrong keys. VK null handle, the number 1, and the pipeline info struct address. A null pointer and our graphics pipeline on the app. Null pointer to p-app graphics pipeline. If that doesn't equal VK success, then we don't have a problem. Okay, I'll just copy this. Printf, add in our null terminator and exit with 9. Failed to create that graphics pipeline, so we did. The VK graphics pipelines function, create graphics pipeline function, actually has more parameters than the usual object creation functions in Vulkan. It is designed to take multiple graphics pipeline creation infos. Alright, that must be why we give it this, pointed to the first one, which is the one for us. Objects can create multiple VK pipelines in a single call. That's cool. So you can set up all your pipeline info structs and create them all at once. The second parameter, for which you pass a VK null handle argument, references the optional pipeline cache object. Oh, interesting. Pipeline cache can be used to store and reuse data relevant to pipeline creation across multiple calls to VK create graphics pipelines, and even across program executions if the cache is stored in a file. Okay. This makes it possible to significantly speed up pipeline creation at a later time. Would it though? I wonder. Because reading a file, surely that's like as slow. Oh, excuse me, I think I'm getting under the weather. We'll get into this pipeline cache chapter. Okay, it's fine. The graphics pipeline is required for all common drawing operations, so it should also only be destroyed at the end of the program. Okay, so in clean up, we've got our pipeline and pipeline layout. So I guess we do that like so. Passing in that graphics pipeline, Cool. Alright, now run your program and confirm that all the hard work has resulted in a successful pipeline creation. You can already getting quite close to seeing something pop up on the screen. Whoa, finally! In the next chapter, sorry, next couple of chapters, we'll set the actual frame buffers and the swap chain images to prepare the drawing commands. Okay. Does it work? It does. Excellent. Alright. That's pretty exciting. So next we are going to be on to drawing. But we'll leave it there for now. This basically another copy and paste video with a minor bit of explanation, but git status, git add main, and git commit, and creates graphics, whoops, pipeline, git push, origin main, and we are good to go. Thanks for joining me for more copy and pasting and complaining. I'll see you next time when we might be able to draw something on the screen. That'll be super exciting.